Okay, so welcome to the lecture on recycling. This is going to be a series of lectures on recycling. Almost in many parts of the world, circular economy is synonymous with recycling. So it's really an important part of the loop. And in this lecture series, we will see the generic principles of recycling. We will also focus a little bit on some of the processes or the steps through which things are getting recycled. Okay, I won't get too much into chemistries and metallurgies because I know that we have a diverse group of students here from different disciplines and backgrounds. So I'll just focus maybe a little bit on how these things go through a series of steps to be recycled. But I will say that we will also focus a little bit on the matter and energy balance and the material flow and the energy flow, because that would be quite important. The exclusive focus on a lot of these lecture series will be on metals, because in decarbonization, if you are going to move away from the sort of challenges of linear economy, we are going to go into, let's say, a metal-based economy. Because for batteries, for solar cells, or for any clean tech devices, metals are inevitably important. So we are going to focus a lot on metals. That plus my background is on recycling metals, so it makes it easier for me to formulate lectures. Anyways, so the first series in this lecture will be a focus on why recycle. What is the significance of recycling? Of course, we have seen it in a larger context. We have seen it in the circular economy, the planetary boundaries, and the footprints context. But let's just take a zoomed in look and then find out what recycling actually offers as important benefits. Okay, let's talk about the importance of metals. See, we have divided the ages depending or based on the discovery of these or invention of these processes to produce metals, right? So we have the Copper Age, the Bronze Age, right to the age of the molecular age, where we have now these crazy nanomaterials and inventions and whatnot. And metal has played really a unique and important role in the construction of our civilization. And interestingly enough, we have an anecdote here. I think this guy is Napoleon III, and it was mid-1800s. He hosted a banquet, a dinner, and he invited guests, and then of course he divided them based on their class. And to the second class guests, he gifted silver cutlery, and to the first class guests, he gifted aluminum cutlery. You know why? Aluminum was expensive than silver at that point of time in history. But why? Because even though aluminum is ubiquitously available, it's not so scarce such in comparison with platinum or gold. But the production process for aluminum hasn't been invented yet during that point of time in history. The Hall-Héroult process, the molten salt electrolysis, came much later. And they weren't able to successfully synthesize or produce aluminum at that point of time, simply because it's a very reactive metal and they couldn't find a way yet. And that's why they considered aluminum to be rare and very novel and difficult to produce, and as a sign of prestige, they gifted aluminum to these first-class guests. Why did I tell this story? Because the conception of scarcity, the conception of criticality is depending on a lot of factors historically and even now. So we will see the concept of construction of this criticality factor in the next lecture, and we will see the various different factors that feed into producing this notion of criticality. So you see, we talked about decarbonization a lot, right? We talked about moving from, let's say, a carbon intensive economy to something else. And for that, we already said that metals will be playing a really huge and vital role. So what is the story behind metal production and emissions. When we talk about primary metal production, what we mean is that we dig up that metal from ore and we go through numerous amount of processes to produce these metals at the end of the day. As of now, in the world, the total energy related emissions is around 33.1 times 10 to the power of 12 kilogram of carbon dioxide equivalents. Okay, and the primary production of metals, that actually has the emission of CO2 equivalents around 3.6. That's 10% of the total emissions. To put this in context, I'll give you a way to think about it. If you plot the countries and the emissions, it would be US at first, China, and then metals. That's what we are talking about here. The primary production of metals is quite energy intensive and emits a lot. But see the figure also on the left to get some sort of context here. If you take the precious group metals, which are relatively very difficult to produce and synthesize because they have to go through a numerous number of steps before they can be produced as metals. The GHG emissions per kilogram is a lot. They are really on the higher side here. But the net emissions from those is not a lot. Why? Because they aren't produced in such huge quantities, which is why you have to focus on two different things. How much of emissions happen on production of let's say 1 unit kilogram or ton of these metals, and how many of tons are we actually producing? So iron, if you see the kilogram equivalents, is not a lot, but that is actually the leading cause of emissions for CO2. Why? Because we are producing really a huge amount of iron and steel. That's why. Let's take a brief moment to talk about steel. You see, people tell that the steel production will come down over a period of time because of this sort of decoupling, but with the facts that we have now, the steel production has always been on the rise. Okay, during the financial crisis, it went down, but it has been on the rise. It may change, but you could see that we are producing billions of tons of steel in the world. And to the right, you see what's called as a Sankey diagram. And Sankey diagram usually, depending on the thickness of these lines, shows the flow of materials and energy. We're not going to go into detail about what is a Sankey diagram, but just to show you that in the construction sector is the maximum usage of steel, and then you have it also in vehicles and industrial equipments. And just take a brief note here about the types of scraps, because during the production of any metals, you have the formation of different types of scraps. We will go into what these types are and how they are related to recycling in the next lecture. So why did I single out steel? Why do we need to talk about steel on the first place? You see, there is 1.85 ton carbon dioxide emitted per ton of produced steel, and it's 3.7 gigaton of CO2 produced in a year. And it's almost 7 to 9% of direct emissions from the use of fossil fuels. So we are talking about something enormous here. I'm just putting things to you in context and showing you the magnitude. So the challenge is a lot. While on the one hand, we want to move away from the sort of, let's say, the emission intensive industries. On the other hand, we have this trap of primary production being really energy and emission intensive. So if you want to actually stick to 1.5 degrees Celsius of global mean surface temperature, as we talked about in the first few lectures, the emissions from steel should be reduced to 80%. So that's a lot. That's really a lot of emissions we are talking about. And you could see what's the energy and CO2 equivalents per year for all these various metals, and of course steel remains at the top. Even though a lot of steel production is based on scrap input, is almost a lot of recycling of steel is a very established process, and we have let's say, huge industrial ramp up of recycling of steel, but we are still in this situation that primary production is happening and then it is energy intensive. Okay, so let's continue down along this line of emissions and metals being a complex story. So on the left, you see the graph of or the picture representation of the copper production in almost in totality. So right from the digging up of the ores and then comminution process such as crushing and grinding of the ores, beneficiation where you improve the quality of the ores, and then you take these concentrates and then put it in acid, and then you pass current and produce metal. So it's a very crude way of putting it, but there are multiple steps that are involved, right? So traditionally we quantified the emissions on these important unit operations such as leaching, electrowinning, which means production of metals, and the comminution processes where you crush, grind the ores. And of course, when it comes to copper, the comminution process, the crushing and grinding are the most emission intensive, of course. But the reason why I show this picture is that there are hidden complexities, hidden emissions inside these processes. I'll give you one example. So people usually use limestone to sometimes increase the pH of the solution and then neutralize something, which means like producing a precipitate, having a liquid solid separation. Okay, so they use limestone. Then you have these production of the calcite from these precipitation processes, and most often you even sometimes dump them or landfill them. Okay, and you would think that as just a waste of resources or waste gathering down at some point in geographical location, but that's not simply about it. The calcites weather over time, they disintegrate over time, and the weathering of these calcites produce CO2. And in one plant, they analyzed that 8% of the emissions in total are coming from the calcite weathering. So you see, an extraction of a metal, that is the primary production processes, has many dimensions. The emissions from its own, the emissions from the unit operations that involve every step from cradle to the product, but also emissions from wastes, emissions from tailings, the things that you throw out that you don't need for the metal production but are stuck with the ores. And then, for instance, in iron production, the major contributor is the usage of diesel in the extracting processes. And you have sometimes the ore located at one point in geographical location, the production units somewhere else, and you have transportation. So you have emissions from the transportations as well. So the reason why I bring this into discussion so much is that when we talk about recycling, we have to talk a lot about how things are produced primarily. What are the unit operations involved? Not just the ones that are visible to our eyes, not just the ones we directly quantify, but also the ores, the tailings, the weathering, the landfills, the emissions from there. But emissions is one part. You have the water footprint, the land footprint, and so much that are tied to primary production. So it's a very complex web, and it has so many different dimensions, the primary production. Okay. Okay, this is a graph from UN Environmental Panel Metal Recycling Report, and there is one statement from that report that has been stuck inside my head. I didn't include the statement in the slide, but it was very important. In comparison with the last century, to dig out the same amount of metal in this century, we are moving materials 3 times more, which means more energy consumption, more emissions. So why are we doing that? Because we have already, for a lot of metals, utilized the chief ores, or the ones which are of very high quality. And the ore grades are going down, as you could see from this graph. I think this is for gold. The ore grade is really declining. What does that mean? It means that to produce the same amount of metal, there is going to be a lot more of energy consumption. So you could see an example from Chile here in copper mining. So in 2001, they had this much of consumption of electricity and fuel per ton of copper ore, and you could see that in 2017 there is 130% increase in fuel consumption and 32% increase in electricity consumption per unit of mined copper. And this is due to the fact that the ore grades are declining. And in addition to this, you also have what's called as the issue of legacy contamination. See the paragraph in the left and guess which year it was written in. So the strongest argument of detractors is that fields are devastated by mining operations. The woods and grooves are cut down, the water has been poisoned, and so on. So it goes on to detail about the issues with mining operations. And it was written in the year of 1556 by a person who argued on both the positives as well as the negatives that are associated with the mining operations. And to the right, you can click the video on YouTube. I think it was in 1990s, the red mud accident in Hungary. It was a serious accident where people also died. So it's not just the energy emissions and all these things that we have been talking about, but also the storage of tailings and the storage of these residues and how they can also be a problem in itself. Okay, thus far we have talked a lot about primary production. One thing I have to say to you is that there is no magic wand that we have as a species to say that, oh, I want to solve the problem of climate change by decarbonizing and moving into a world where metals will obviously be dominant, but it's also energy and emission intensive that the primary production of metals entail. We don't have a magic wand to immediately solve this problem because we will need these metals for our clean tech applications, and this simply means that primary production will have to go on. So if these are the cases, how can we best address the problem? And in here you see the concept of embodied energy. So a theoretical energy is like the amount that you have to give to separate, let's say, a metal from its oxide or a sulfide form to form the metal. Okay, so imagine titanium dioxide, you want to form titanium metal. How much of energy would you actually need is the theoretical energy. The actual energy is how much that we practically use to produce metals. And see the ratio for these things. And for some metals, it's off the charts, right? So it's a lot, more than 25 times. So a lot of these energy has to be supplied to meaningfully extract the metals from the ores. And it's not straightforward. So as I have indicated in the past, we have so many different processes as intermediate steps before we could produce these metals. That's where the concept of embodied energy comes in. So how much of energy do we actually need to go from the cradle, the ore, to the production of the final product, that is the metal? That's the embodied energy of that particular metal. Okay, I know some of you might be already unhappy seeing such a list of equations in this slide, but worry not. It's quite a simple equation, and there is a reason why I included this in this particular slide. So we want to understand the concept of embodied energy properly, right? Let's say that from an ore to a metal, we have 4 stages. The mining stage where we dig up the ores, and then we have the beneficiation stage where we improve the concentration of the metal that we want to produce in the ore. So we have an up concentration stage where we remove the impurities and then, let's say, increase the concentration of the metal that we want to extract in the next stages. And then let's say we have 2 chemical processing stages, and at the end of these 4 stages we get the metal. Okay, so as I told you in the very beginning of the slide, it's important to know the material flow as well as the energy flow in any production process, be it primary production or be it recycling. So to know these two things are very important. So this set of equations simply give you the matter flow and the energy flow during all these processes, okay? And then you get the final equation. So I suggest and encourage you, and I insist that you go through all these variables in these equations. So you have the ore grade, you have the energy consumption during each stages, and the fraction of energy, sorry, the fraction of material recovered in each stage. Okay, so at the end of all these things, you have an equation here, and this equation gives us a clear idea of the concept of embodied energy. So the embodied energy, or the energy per ton of value in the products, is simply a sum of three things: the energy that we require in the mining and beneficiation stage, and the energy that is required in the chemical processing stages 1 and 2. That's it. And what this is, how is this connected to all the other different parameters? So you could see that the lower the ore grade, that is, we have already seen from the UN environmental panel that over the years in the century, the ore grade has decreased, right? So lowering the ore grade increases the embodied energy. Okay. At the same time, if you let's say have a lot of waste rock that is produced together when you dig up the ore that you want to dig up, then that also increases the embodied energy. Okay, and this lowering of this ore grade as well as the increase of production of waste together with the ores, these two things are connected to the mining and beneficiation steps, right? So the higher energy consumption during mining and the beneficiation steps are connected really closely with the ore grade. But the chemical processing steps and the energy consumed, or the energy required during the chemical processing step, has nothing to do with the ore grade, okay? And that is simply shown through these equations. So what is the energy required in chemical processing step dependent on? It's very simple. If you recover low amount of materials, that is, lower the recovery, higher is the energy consumed during these chemical processing stages. So what do we want? We want a really high ore grade. We want to generate less waste rocks when we dig up the ore. We want to recover as much as materials as it is possible in these chemical processing stages, highly efficient processing stages, right? So that's what this equation shows. It gives us clearly the concept of embodied energy. Embodied energy is, let's say, it signifies the things and it embodies the things that are present in these stages. Okay, so all these multiple stages from the cradle to the product gives us an idea of the concept of embodied energy. Okay, so just to continue along this line and to give you an example, you can see for aluminum, copper and steel how much of energy is required for all these different stages for mining, beneficiation and two different chemical stages. And you could see something interesting here. You see the in terms of megajoule per ton for beneficiation for steel, it's a lot, right? But at the end of the day, the total embodied energy is less in comparison with, let's say, aluminum or copper. Why? There are many reasons, but see here the ore grade. Okay, so all these things are interconnected with one another. So if you go through this table, you'll get a better idea of how much of energy is consumed during each and every stage and how you can compare with one metal to the other. Okay, so I'm going to give you guys a small exercise which will be very illuminating and then it informs you much better what we are talking about here. So you see these are the primary energy that is required per kilogram for all these different metals, right? And you could refer this table for the exercise. I have a question to ask. So the titanium has a theoretical free energy of formation of 907 kilojoule per mole. So for 1 mole, this is the total energy. So this is simply the energy that you need to provide to produce titanium from its oxide, okay? But we know that the primary energy consumption is 500 megajoule per kilogram. So this is the actual energy consumption. And I gave you the theoretical energy of formulation. So with this, of course, it involves a little bit of math. Give me the approximate percentage of efficiency of its production. Okay, once you see how efficient or how inefficient the process is, then it gives you an idea of what is at stake. Okay, thus far I showed you the various aspects of primary production of metals, that is the different stages that are involved in primary production, the lowering of the ore grade, the emissions that are associated with the primary production. All of this only to bring you back to this particular slide, and this would end our lecture for today. So you see in the left the percentage of savings when it comes to energy while you try to recycle a metal and in comparison with the primary production of the metals. And you could see here a lot of metals, when you try to recycle, it offers substantial saving when it comes to energy consumption. So you lower your energy consumption a lot. And here you see concretely an example for steel. When you try to recycle steel to the electric arc furnace route, you have this much of energy consumption. But when you compare it to the primary production route, that is using a blast furnace, you could see an enormous energy consumption. So you save the energy a lot. You reduce the energy consumption a lot when you try to recycle. This in turn also translates into reduced emissions. Okay, so for instance, for copper, you could see for recycled copper, it's 0.1 ton of CO2 per ton of copper when it's simply recycled. But when it comes to primary production, you see 3 ton of CO2 per ton of copper from ore. So from this, you could already see the salience and significance of recycling. It contributes to you in the whole context of circular economy through reduction in energy consumption and also through reduction in emissions. But what is also important to know why this is happening, okay? As I told you, the primary production process in itself is complex and it has to deal with huge amount of impurities. It has to get rid of huge amount of impurities through various stages, okay? And with the lowering of ore grade historically, it means that you need to supply a lot more to get the same amount of metal that we got in the previous century. So I showed you data for all these things, right? Recycling is taking a metal away from let's say a purer stream, because we have already gone through a lot of this and then put the metal in a place where it is up concentrated already. Okay, so it's much simpler when you compare with primary production to recycle something, and that's why you have a reduction in energy consumption as well as a reduction in emissions. Having said all these things, recycling isn't a panacea either. It's not a one-stop solution that we could simply do and then get away with all the problems. We are going to see what are the modern challenges when it comes to recycling. And we are also going to see that only with recycling, it is never going to be enough. So primary production is always going to be a key component in metal production. So we will have this wider debate about different aspects of recycling in the forthcoming lecture. For now, I end you this lecture with the salience of recycling. So have a good week.